Hey, welcome to this story about waves of activity, and in particular the involvement of a late wave of activity in mouse primary visual cortex for perception. As many people observe, for example, in the human visual system, you see an early peak of activity that's mostly sensory driven, probably from the thalamic bottom-up inputs, and a late wave of activity that really corresponds to perception and whether actually humans report the stimulus. You can also see this actually in the mouse somatosensory system and many other findings. And there's two basic questions. One is what is the nature of this late activity? Does it mostly correspond to movement that goes all the way back to primary sensory areas, as has been increasingly reported recently? And what is the causal relationship to perception and perceptual report, as other studies try to silence this late part and they find contrasting evidence for whether it's causal or not. So we try to develop a task that separates this early and this late components, and we had head-fixed mice detect changes in the orientation of a drifting grating or changes in the frequency of a tone. And we had three cohorts. One cohort that was basically naive, not trained to detect anything. We had one cohort that was trained to detect changes in the visual orientation, but not the auditory. And we had one cohort that was responding to both visual changes, but also auditory changes. And we find that the performance on the visual domain was the same for these unisensory, multisensory trained mice. They responded to the same exact changes in the visual gratings, but their response latency was longer for the multisensory animals. And if we record in V1, we find a mixed bag of responses. We find neurons that respond to the visual stimulus, regardless of whether it's a hit or a miss. And we find neurons that show a second wave of activity that really corresponds to whether the animal is actually perceiving the stimulus and shows a hit. And if we average over all neurons, we see that there's no such late component in the naive animals, but there is such a component in the unisensory and the multisensory trained animals, so in the trained animals. And if you look at when you can really say that there's a difference between hits and misses, so when this late activity starts, you find that this late activity starts earlier in the unisensory trained mice, and also that this correlates with the reaction time. So this also suggests that it's strongly related to the movement onset, and in the poster we go into detail more about the relationship with movement. So what we try to do is silence this late component by temporally specifically inactivating V1 with optogenetics. And if we silence from 0 milliseconds, the activity drops instantaneously. We can also silence after 200 milliseconds when the first component has been passed, and we silence later activity. And we find that the early sensory component, if we silence that, then of course visual performance, depending on V1, goes down. But silence in the late component only affects the multisensory condition. And specifically, we find that the effect of silence in this late component really depends on the reaction time, how fast the animal is, with the slow animals being affected most. And we confirm these results in a very different task, a visual tactile sight detection task, and we can explain you more in the poster. So to try to get at the mechanism of why V1 is still involved at such a late time point, so after 200 milliseconds, we investigated the population structure and computed pairwise noise correlations. And if we look at the noise correlations in really fast trials, the noise correlations go down, and they go down really early, whereas in mid and later and slower trials, these noise correlations start decreasing later, and this correlates with the reaction time. We also find that noise correlations go down just before we photostimulate, and that is enough to still allow a visual hit, whereas misses don't show this decrease. And also activity increases just before hits in photostimulation. So this suggests that by comparing these task variants, we find that increasing the task demands in a multisensory context delays the reaction times and extends that V1 is still necessary, causally necessary at such a late time point. We also find that decorrelation of V1 population activity could improve the readout of communication with downstream areas. And we'd like to thank this joint project between Matthijs me, Jean, and our collaborators.